So, good afternoon, one and all present here. So here we are starting our session 2 of online STTP, 1 week online STTP on optimal power system incorporating renewable energy sources. Our speaker is same as of the morning session, Professor Mohan Kole from University of Agder, Norway. I have given the elaborated introduction about this in earlier lecture also, so we will not be repeating this again. So the topic for this session is integrating renewable energy systems with energy storage and hydrogen. So I would like to invite Sir to please enlighten us with your presentation for the session.
Thank you very much, Nidhi. Yes, I'm sharing the screen. I hope it is visible now.
Yes, sir.
Yes, sir.
Yeah. So thank you very much, and welcome to the second session. So I will continue my lecture from the session 1, and then basically for the session 2, the focus is on integrating renewable energy system with energy storage as electrolytic hydrogen. And before the break, I was sharing my experience of different projects related to integrated renewable energy system. And now, before going
Just
to
a
the
minute.
key
I would
theme of
like to request. I would like to request folks to please mute the other participant as there is some noise is coming.
So before going, I would like to share that there was one more project when I was working at the University of Dundee, Scotland. It was on decentralized off-grid electricity generation in developing countries and how the business models can be developed for the off-grid electricity supply. And this project was also funded through competitive research application from EPSRC and two UK universities partners and two Indian organizations. And the learning from this project, from the renewable energy point of view, like how we have to develop the business models, how we have to develop the business model for off-grid electricity generation, and especially taking into account the Indian condition. So in this project, the local scenario of local availability of renewable energy sources with reference to the grid availability and its energy economics analysis over the lifetime of the project have been had been completed in this project, and the project outcomes have been very good. So now we will come to the main theme of today's today afternoon's lecture. So it is a solar hydrogen energy system. And before going in depth to the lecture, I will mention you that we can store the energy in many forms. Okay, mainly we are considering the energy storage in the electrochemical forms, and in the electrochemical forms we have the battery banks, and there is another option that is hydrogen. So hydrogen can be a very good energy carrier for long-term energy storage from the renewable energy sources. And by considering that point, when I was working at University of Jyväskylä, Finland, as well as Hydrogen Research Institute, Canada, I had the opportunity to develop or to build practical demonstration system where we can integrate solar photovoltaic system or the wind energy system for storing the energy in the form of electrolytic hydrogen. So this hydrogen is having very high mass energy density and is very good medium as an energy carrier. And now people are talking about, now the hydrogen economy is getting coming up, and people are talking that how we can utilize the existing infrastructure of natural gas for injecting the hydrogen in the system, or maybe converting the electricity generated from the renewable energy sources and producing the electrolytic hydrogen and injecting into the natural gas system and making it hydrogen. Right? And then when we have the hydrocarbon gas with more percentage of hydrogen, so naturally we are going to reduce the CO2 emission and we can get much more energy output. It's much better climatic condition. So considering this point, here you can see that this system has been developed at the University of Jyväskylä, Finland, when I was working as a research director, Renewable Energy Technology Division in the University of Jyväskylä. So here you can see that in this picture, the wind turbine and the solar photovoltaic system, they have been considered as the primary renewable energy sources. And considering the power conditioning devices here, the energy which are coming from these primary renewable energy sources, okay, with reference to the electricity grid, have been provided to the electrolyzer. And this electrolyzer, basically, it is giving us the purified hydrogen or electrolytic hydrogen, which has a very high purity, maybe 99.999%. And of course, then through our electrochemistry, we know that oxygen is also going to be byproduct that. When we are storing the energy in the form of hydrogen, so this hydrogen can be stored in the gaseous form. Okay, we can compress it, store it. Either we can store it into the metal hydride form also. Okay, so then when we are storing this energy in the form of hydrogen, okay, then we need to reutilize it for producing the required amount of electrical energy. So for that purpose, here in this project, proton exchange membrane fuel cell have been used. And this, in the proton exchange membrane fuel cell, the stored hydrogen has been utilized as the fuel. Okay, and the oxygen, which was a byproduct from the electrolyzer, it has been used as the oxidant in the fuel cell. And we know that when the fuel cell it is operating, right, it is going to produce the electrical DC electricity, at the same time heat also, and the output from this proton exchange membrane fuel cell will be the pure water. So this system has been developed in the at the University of Jyväskylä, Finland. And here in this system, there are a lot of opportunities for the students also for doing the project work. For example, some students, they did the work on electrolyzer characterization, modeling, and analysis. Similarly, the fuel cell characterization, modeling, and analysis have been also done here. Okay. And then when we are connecting all this system, so of course we need to have the data collection. So here control and data association system have been there. And this, then we can analyze this data. At the same time, you might have noticed that now people are talking hydrogen fueled vehicles or maybe fuel cell vehicles. And you might have seen that many car manufacturing company, for example, Toyota, Hyundai, Mercedes-Benz, BMW, they are actively moving towards to have the future vehicles based on the fuel cell. Even Hyundai and Toyota, they are launching their vehicles into the market, and Toyota Mirage vehicle based on fuel cell, they are already running into the market. So considering all these points here, when I was working in Finland, we have one technical college, what we call it in India as a polytechnic. They helped us in developing one single passenger fuel cell based car. So here you can see that this is a single passenger fuel cell car in around 2004 time or 2004 or 2005. And I'm demonstrating this hydrogen fuel cell car in international summer school here. So here you can see that there are many international participants who were attending my course on hydrogen technology, and as a part of that course, here I am in the white shirt, I was demonstrating this fuel cell car to the participants. And in this car, the proton exchange membrane fuel cell have been used. And for this car, the hydrogen which is generated through the electrolyzer, it was stored into the metal hydride form, and it has been kept here. So here you can see that this solar hydrogen energy system had been developed in 2004-5 at the University of Jyväskylä, Finland, and we tested this system for the application of the protonic change membrane fuel cell for a single passenger car. And from the student point of view, students, they did a lot of experiments on electrolyzer characterization, modeling and analysis. At the same time, they also did some work on fuel cell characterization, modeling and analysis here. And we collected the data from all this system. So here you can see that, right? So if we want to move towards the hydrogen based economy or hydrogen based energy system, and we want to produce the electrolytic hydrogen from the renewable energy sources, or maybe green hydrogen, which we can say, so we need to adopt such type of system. So that was a quite interesting. Now I will then another project which is again related to the protonic change membrane fuel cell, because we are in the same project where we want to utilize the learning from the previous project to the new project. And in the previous slide I mentioned that this fuel cell is going to have very good application in the automobile sector. So in automobile sector, we know that we are going to have very dynamic loading and transient loading also. So due to that, we need to do the analysis of protonic change membrane fuel cell modeling for dynamic load. So when I moved to the University of Dundee, Scotland from University of Jyväskylä, Finland, then I had the opportunity to make an application for competitive research grant to the Northern Research Partnership Scotland in cooperation with the Robert Gordon University Aberdeen, that how we can do the analysis of protonic change membrane fuel cell for dynamic load. So that project has been very good, and it is quite relevant to the present situation when most of the car manufacturers, they are trying to move towards the fuel cell vehicle, and they are considering this electric vehicle based on the batteries, right, for the medium term, but for the fuel cell vehicles they are considering from the long term point of view. So here you can see the research work which I did in around 2006-7 at University of Dundee is going to be used nowadays in by the car manufacturer, or maybe in simple way the outputs from this project are going to be useful for the industrial community as well as the academic community for developing or analyzing the fuel cells for the automobile applications. So that has been very interesting. And then this slide I will skip, right. Then another, which is the slide which is very interesting and related to the second session of our today's lecture, that this fuel cell system can be used for the stationary power generation applications also, okay, not only for the automobiles. So if we consider the fuel cell for stationary application, then solid oxide fuel cell is going to have very good appropriate application due to its combined heat and power capacity, and we can utilize the natural gas as a fuel due to its higher operating temperature. So considering all these points, the fuel cell can be used as a distributed generator within the distributed network. Therefore, it can contribute towards the power system stability for the microgrid or the distributed network. So now we are talking about the smart system, distributed network and distributed generators also. So here you can see that when I was working in 2003 at the University of Quebec, Canada, I developed this successful project which was funded by National Research Council and National Engineering Research Council, Canada. And now we are coming to that stage now right? So here you can say that we have, while doing any research or while doing any academic activity, we need to make a plan that what the research we are going to do, how it will be used within the industry or within the energy system, let's say after 10 years or 15 years. So based on that, we have to make our vision, and based on that, we have to develop the project. So here you can see that the project which I have been working from 2001 on the hydrogen energy system, and now if we see the latest news on the in the energy area, right? So most of the big energy companies, they are moving towards the hydrogen system, right, or towards the hydrogen economy. So I feel very happy that the work which I did, let's say 2 decades before, is now going to contributing towards the sustainable development of the society, where we can use hydrogen as an energy carrier. Okay, so now here I'm sharing you a very simple slide from the European Union. It says that by 2050, our oil-based economy should be replaced by the hydrogen-oriented economy. And by 2050, it says that the hydrogen should be produced from the renewable energy sources, means that our society is going to become decarbonized hydrogen society. Considering this point, let's say if we have to move towards the hydrogen based economy, so how we can get the hydrogen? Hydrogen is going to be an energy carrier, that we know that, okay, and it is a good medium for storing the energy, okay, as well as transporting the energy or transmitting the energy from one point to another point, in the same way as we are using high voltage transmission lines also. So basically hydrogen is going to be as an energy carrier. So when we want to make hydrogen as an energy carrier, so there is a potential for producing the hydrogen through the renewable energy sources. But at this moment, around 90% hydrogen is coming from natural gas reforming. So basically we have to use very high temperature, and hydrocarbonic gases is going to be reformed into the reformed, and then we can collect the pure hydrogen. And for the reforming process, we can use the coal gasification also, we can use the poly biomass also, or the solar thermal system also. But if we consider the electrolysis through the renewable energy sources, for example, solar photovoltaic, hydro, wind, then we can get the pure hydrogen. Even we can use the nuclear electricity also, and nuclear heat can also be used for the gasification or the reforming process of hydrocarbon gas for producing the hydrogen. But if you take the previous slides into account, in the previous slide it has been said that by 2050 the hydrogen should come from the renewable sources. So it means that we need to go here on the renewables, solar photovoltaic, hydro, wind production through electrolysis, then get the hydrogen. Let's say we analyzed the different sources for the production of the hydrogen. Then we have to consider that how this hydrogen is going to be used in the different applications. We know that hydrogen can be used in internal combustion also, internal combustion engines also, and that has a good application in the transport sector. And then the hydrogen can also be used in turbines also, or in process industries also. But now the more focus is moving towards the fuel cells. In the fuel cells, when we are using the hydrogen as the fuel cell, then fuel cells can be used in the transport applications also.
So there is a request. If you can please increase the volume. Actually, in YouTube Live, the volume has been reduced. So if you can please increase the volume, then we can.
Okay, my computer volume or.
So your computer volume maybe if you are connected to that.
Yeah. So I will speak otherwise little loudly maybe.
Yes.
Yeah, very good. And then when we have the fuel cells, then fuel cells, if you get any problem, just please tell me, okay?
Okay.
Yeah, please. Fuel cells then we can use in the transport sector also, and building also, and industry also. So here the fuel cell, depending on the hydrogen, let's say if we are going to utilize the pure hydrogen, then we have to take proton exchange membrane fuel cell. But there are many different type of fuel cells also, depending on the type of the fuel which we are going to use. So that I will cover into the next slide. In the fuel cell, let's say if we are considering into the building side, then we have the application commercial, residential or tertiary applications also, and in the poly generation also. So with reference to the building side or the poly generation side, I have been associated with the Mie University, Japan, where I am working, that how we can utilize or how we can install the fuel cells at the individual houses for producing electricity and utilizing the heat for the heating purpose. So the articles or the research outputs from that project, they are publicly available in the open access journal also. So if you Google my name, and maybe you can put Japan also, in addition to that, you can get the relevant articles as the research output from that project. Now, as I mentioned earlier, the fuel cell. So fuel cells depends which type of fuel we are going to use. So mostly in our mind, it comes to the hydrogen. Let's say if we are getting the hydrogen, and hydrogen is pure, right, 99.99% pure, then that hydrogen can be directly used in proton exchange membrane fuel cell, or maybe even alkaline fuel cell also. But uh, I mentioned earlier that we can inject the hydrogen into the natural gas pipeline, where we can increase the percentage of the hydrogen and reduce the percentage of carbon, right? So then it becomes the hydrogen. So then it comes under this category where we can have the biomass or hydrocarbon gas. So then that hydrocarbon gas with higher percentage of hydrogen can be used into the solid oxide fuel cell. And solid oxide fuel cell, it is going to operate at very high temperature, around 700 degrees centigrade. So it has a good application for the combined heat and power. Okay, so under that scenario, right, we can utilize it more like a distributed generator, where we need the heat also on the electricity also. So depending on the fuels, or depending on the type of the technologies which we are going to use, we can categorize the fuel cell in different sections or different types also. So then another fuel cell, which is a molten carbonate fuel cell, where also we can use the natural gas. Okay, and let's say when we have the natural gas, but if we can put the reformer, high temperature reformer, then we can use that pure hydrogen through reforming process in proton exchange membrane fuel cell also, and phosphoric acid fuel cell also. Then another small capacity fuel cell, that is a direct methanol fuel cell, where we have ethanol. Then when, let's say, depending on which type of fuel we are using, depending on the capacity, okay, then we have to identify the different applications of the fuel cells. So here you can see that we have the portable application, transport application, stationary application. Portable applications for small capacity, or maybe let's say charging our mobile or maybe the laptop, then direct methanol fuel cell, they are the very good candidates for that. But if you consider for the transport application, and we consider especially the road application, then the proton exchange membrane fuel cell is having very good application. Similarly, for the maritime applications, okay, so solid oxide fuel cell can also be used, or even proton exchange membrane fuel cell can also be used. Now you might have seen that some of the aerospace industries and aeroplane manufacturers, they are also considering to use the fuel cell for powering the aeroplanes or the aerospace applications, right, or the air applications. So then they are considering proton exchange membrane fuel cell for that purpose. And for the stationary application, it can be for the residential and industry. So residential purpose, we can use proton exchange membrane fuel cell because its operating temperature is quite low. But now the people are also talking about the solid oxide fuel cell, because in most of the houses we have the natural gas pipelines. So we can use the natural gas pipelines directly for fueling the solid oxide fuel cell. But here the problem is that it is going to operate at very high temperature. Then we need to put some heat exchanger for reducing the heat at the low quality level, or maybe utilizing it in other purpose also. And similarly, then This fuel cells, they can be used for the industry application for the distributed power generation. So here you can see that in both slides we have seen that how the hydrogen is going to be produced, and when we want to utilize that hydrogen into the fuel cell, then how the different options are there. Okay, then this is really a very good point. When we are talking about the hydrogen economy or moving our system towards the energy carrier as hydrogen, means we are moving towards the hydrogen economy and we want to replace our oil-based economy. So there are a lot of challenges behind that, and these challenges may help you in identifying some research topics also, or some industrial projects also, or maybe in developing your course curriculum also. For example, here the main thing is that how we are going to produce the hydrogen, right? So that is a big challenge. Then another big challenge is that how we are going to store the hydrogen, which form, whether we are going to use compressed form, metal hydride form, or cryogenic form. Again, that is a big challenge here. Then another thing, very interesting thing, we are going to produce the hydrogen at a particular location and we have to transport it or deliver it at another location. So for delivery mechanism has to be there. That is again very big challenge, whether it is going to be gas pipelines or maybe through the tankers in the compressed form or in the metal hydride form, so on and so forth. Then when we have the hydrogen and then we need to utilize it into the fuel cell, so of course then we need to work on the fuel cell. And I mentioned that this pure hydrogen is having a good potential in proton exchange membrane fuel cell, and as all of us we know that proton exchange membrane fuel cell is very costly, as it is going to it is using platinum as a catalyst. Due to that, its cost is very high. And then of course we have to work very hard that there should not be any leakage of the hydrogen, because if you consider by the volume in a particular room, 2% by volume, the hydrogen is going to be highly flammable. So when we are talking about all these different subcomponents, let's say, then we need to do the technology validation for that one. So there is a lot of time or a lot of efforts are required for research and development of this technology. Then let's say when we are in a position to do the research and develop the technology by doing the technology validation, then another thing which comes very into account that how we need to integrate all this. So system integration and analysis. And on top of that, then we need to consider about the safety, because hydrogen is highly flammable. All of us will know that. So safety should be on the top priority here also. Then when we are talking about hydrogen economy and we want to make this hydrogen system, and then of course then we need to develop some standards and the course also. So here you can see that there is a lot of potential for doing further research work on electrochemical energy system related to the hydrogen, where we can consider how we are going to develop, how we are going to produce the hydrogen, in which medium we are going to store the hydrogen, what type of delivery system should be there, which type of fuel cell we are going to use, how we are going to do the technology validation. And here you might have seen that then all these different system components, they are having very different operational characteristics also. So when this heterogeneous system with different operational characteristics are there, then how we are going to do the integration and analysis also. Then of course we need to work on the safety and the standards. So here this slide, it looks like very simple, but it gives you very high level ideas on developing new academic curriculum, new industrial projects, or new research activities on the hydrogen economy. And each and every activity what it has been, I was explaining here, right? So required a lot of efforts and inputs on that. Now I will share with you one of my experience on integrated renewable energy based hydrogen system for decentralized power generation. So in this system, these primary renewable energy sources, solar photovoltaic system and wind, they have been considered. And idea is that whenever we have excess energy from these primary renewable energy sources, then how we can store it in the form of electrolytic hydrogen. Okay. And in this project, it was a demonstration project and of course a lot of learning also. This system has been developed considering a standalone system, and in this standalone system, a typical cold climatic area 5 kilowatt load have been considered, and considering that 10 kilowatt wind turbine and 1 kilowatt solar photovoltaic system have been used as primary renewable energy sources. When these primary renewable energy sources, they are producing the excess energy with reference to the load, then that has to be stored in the form of electrolytic hydrogen as a long-term energy storage point of view. So that has been covered here in the hydrogen production and storage system. Now here there should have been one point which I mentioned, which I missed to mention here, that is when there is a deficit of the primary renewable energy sources with reference to the load, then stored energy in the form of electrolytic hydrogen has to be reutilized through the fuel cell to fulfill the electrical load demand. So then here the point should have been hydrogen utilization and subsystem. That point you please consider here. Then when we have this system, then we need to work on this system performance, how the system is going to be performed. And then when we have the wind, when we have the solar photovoltaic system, when we have the electrolyzer, when we have the proton exchange membrane fuel cell and the load also, and then we want to operate them, and objective is to store the excess energy in the form of electrolytic hydrogen and to reutilize the stored excess energy in the form of electrolytic hydrogen through proton exchange membrane fuel cell for producing the electrical energy. So we need for this system some control system, okay, and power conditioning devices also, because that is very important. Every system or every component, every subsystem and every component, they are having very different operational characteristics, and we may need to define some logic when we need to store the energy and when we need to utilize it. Okay? So for that we need to have some control system for that. Then when we want to have this control system, or when we have this control system and when we are testing it, then of course then we need to do the operation and performance evaluation also to learn from the results. And based on the results, then we have to find out some conclusion whether such type of system are feasible or not, and if feasible, where are the problems, which are the problems, how we have to rectify them, or what mistakes we did, right? So all these points have been considered in this project. Okay, now some of you may get the idea or might have came in your mind, like energy storage in the battery bank is quite straightforward compared to the hydrogen. So why not we should go for the battery bank? Yes, that is also true. Battery bank is quite good for the energy storage from the short-term point of view. But if we consider from the long-term point of view, then hydrogen as an energy carrier is having a big potential. Okay? And this hydrogen then having many applications, not only from the electricity point of view, but also it can be used in the process industries. It can be used from the transport sectors also. So it can contribute in many sectors for sustainable development, or maybe in a simple way contributing towards reducing the carbon emissions on this globe. Okay. Now here another point which you may come in your mind. Most of the technologies what we are discussing here, they are available into the market. But the big challenge is that how to integrate them, right? So that is a big challenge, and how we have to control them and operate them. So for that, then we need to design appropriate control strategy, and with that appropriate control strategy, we can test this system and see that how such type of system can work. So all these factors have been taken into account in this project. So now this is a very nice and very interesting diagram here, and I try to make it very simple. Okay, so here you can see that this is the wind turbine, and this is the solar photovoltaic system, and this is the electrical load. Okay. Now, previously I mentioned that whenever we have the excess energy from these primary renewable energy sources with reference to the load, then that excess energy has to be stored in the form of electrolytic hydrogen. That is the key objective. Okay, and that is the future now, and most of the companies, they are working on it. If you consider the hydrogen vision plan of Korea, Japan, Australia, Europe, so in every plan or in every vision document, only they are considering to produce the hydrogen, right, from the renewable energy sources. Now you can see that I'm working on this project from 2000 or on the hydrogen system from 2001, and now let's say after 2 decades it is coming into the market. So we don't need to lose our hope if we are working on any project and which we don't see the immediate market potential. But sometime, right, we have to see the vision, like how the system is going to be implemented and how it is going to contribute towards the society development or towards the energy system development and like that. So now coming back to the key point here, when we have the excess energy from these primary renewable energy sources with reference to the load, right, then that excess energy has to be stored in the form of electrolytic hydrogen here. Okay, now when there is a deficit of the renewable energy from these sources with reference to the load, then we have to utilize this stored hydrogen through the fuel cell for producing the required amount of electric energy for fulfilling the load demand. Now here you can see that one reference point has been taken. This reference point or the reference bus has been taken as a DC bus. Okay, and on the DC bus for the short-term energy storage battery bank, they have been used. Okay, and this battery banks or the DC bus energy level has been taken as the reference point for starting the operation of electrolyzer and the fuel cell, and by taking into account there should not be any simultaneous operation of both electrolyzer and the fuel cell. Okay, that is the key point here. So for that we need to define a reference point here, and that reference point has been taken as a DC bus here. Why we have taken as a DC? Because these electrochemical devices, which are the key components of this system, they are basically operating on the DC voltage or on the DC energy level basically. So that's why we need to consider the reference level as a DC bus, and for that we use short-term energy storage as a battery bank. So now coming back to the point here, let's say we have the excess energy from the primary renewable energy sources, with reference to the electrical load, then that excess energy, okay, then that excess energy has to be transferred to the electrolyzer. Okay, but how it has to be? Then here we need some controller here or someone who can take the decision, and all decision has to be taken automatically and with using some instrumentation or the controls. So here master controller, it takes the information from the primary renewable energy sources with reference to the load, how much excess energy is available, and considering the energy level at the DC bus, then this master controller, it sends the information to the microcontroller. So this microcontroller is basically only for the electrolyzer, and this microcontroller then sends the information to this buck DC-DC converter, or let's say power conditioning device, for managing its pulse width modulation, for transferring the excess energy from DC bus, which is basically coming from the primary renewable energy sources, to the electrolyzer. Okay, then this electrolyzer is going to produce the electrolytic hydrogen, and then this electrolyzer is at the atmospheric pressure. So when it is atmospheric pressure, this electrolyzer is producing the hydrogen here in the buffer storage tank at the atmospheric pressure. And when we are not compressing the hydrogen, so we are putting this hydrogen at the atmospheric pressure, so very soon the tank will be full here. Okay, so when the tank is full, then we need to transfer this hydrogen here to the hydrogen tank, then we need to compress it. So here then we have the compression, and this compression compresses the hydrogen or the electrolytic hydrogen at a particular pressure and stored here into the hydrogen tank here. Is it okay to understand? If you are not able to understand, or if you have any communication problem with me, please tell Neeti so that she can intimate me. Yes, sir, is there is some problem, so I can improve that. Okay. Now next point, let's say when we have deficit of energy from the primary renewable energy sources with reference to the electrical load, okay, then naturally what we stored the energy in the form of electrolytic hydrogen has to be reutilized through the proton exchange membrane fuel cell for producing the required amount of electrical energy. Then here the master controller, it takes the information from primary renewable energy sources as well as from the electrical load side also, and energy level condition at the DC bus. Then it sends the information to the microcontroller, and microcontroller then starts the fuel cell operation, and then fuel cell utilize the stored hydrogen as the fuel for producing the electrical energy. As all of us, we know that this is an electrochemical device. It is going to produce the energy at the DC and at a particular voltage level, and this DC bus is going to have another voltage level, so we need to boost converter here, and to transfer that energy from fuel cell to the DC bus and to the load, then this boost converter it helps, and then boost converter controller, or let's say it's modulation or PWM modulation, whatever you call it, it is controlled through this microcontroller here. Okay, and at the same time, depending on the requirement of the energy, the hydrogen consumption, that is the fuel consumption for this fuel cell, is also controlled here. So now here you can see that with reference to the available energy from the primary renewable energy sources, with reference to the load, and considering the defined energy level at the DC bus, this master controller can take the decision for starting either electrolyzer or the fuel cell, but not both simultaneously. Okay, and making this system autonomous or standalone operational. Then another question, it might have been came to your mind while when I was explaining the previous slide. So in that slide, I mentioned that we can use the hydrogen into the internal combustion engine also. So in one part of the project, we used here internal combustion of engine, and internal combustion of engine, we used the hydrogen fuel here, and then in place of proton exchange membrane fuel cell, we can have this hydrogen powered generator also, and accordingly then we can supply the electricity to the load. So here, I mean, you can see that all these systems, they are having very different operational characteristics. Now I will explain you every component one by one. This wind turbine, it was having the capacity of 10 kilowatt. It was permanent magnet synchronous generator. It was producing variable voltage, variable frequency output. Here it was a solar photovoltaic system. All of us, we know that through maximum power point, again it is coming the DC output. Okay, and here variable voltage, variable frequencies, but here we have taken as a DC bus as a reference. So we need to regulator to convert it into the appropriate DC voltage so that it can be well integrated on the DC bus. This electrolyzer, it was alkaline electrolyzer having the capacity of 5 kilowatt. It was manufactured by Stewart, and this electrolyzer is having the operational voltage little higher than the DC bus voltage. Okay, so so then we need to have here a DC-DC converter for transferring from here to here, and in this electrolyzer it was having a buffer storage tank, hydrogen storage tank at atmospheric pressure. when this atmospheric pressure storage tank of hydrogen, it gets cooled, then compression, it was starting automatically and compressing the hydrogen at the particular pressure of 8 bar. Okay, and here you can see that this hydrogen storage tank, it was out of the lab. Okay, not within the lab. Okay, and of course the pipelines were there. Then when we don't have the enough energy from the primary renewable energy sources, as well as the energy level at the DC bus is at little lower than the level when we started the electrolyzer, then we need to utilize this hydrogen. So for that, this master controller, when it sends the information to this proton exchange membrane fuel cell, this proton exchange membrane fuel cell, it was having the capacity of 5 kilowatt. This was manufactured by Ballard Power System, and then it utilizes the hydrogen as the fuel at the 8 bar. Okay, and of course then we need the oxygen or oxidant also. So in the first phase of the project, compressed air that has been used as the oxidant as in this proton exchange membrane fuel cell, when it produces the electrical energy, it has been transferred to the bus through the boost DC-DC converter here. So here you can see that how these different components, they are integrated here. This electrolyzer is having very different operational characteristics. This fuel cell, it is also going to have very different operational characteristics. And we know that this PAM fuel cell, it is operating around 70 degree or 80 degree centigrade, but we used only the electricity for here, and we didn't put any heat exchanger for extracting the heat or utilizing the heat for other applications. And then of course at one stage we removed this proton exchange membrane fuel cell and we put internal combustion engine. So this picture, single line diagram or the picture, is going to provide you very good high level overview that if we have to move towards the hydrogen economy and we want to have the electrochemical energy system into the picture, then the learning from this project or learning from the this system is going to be very useful, not only for the academics but also for the industry. Now here then another point which has in another way the previous diagram or previous slide have been explained here. So here you can see that how this single line diagram have been represented, right? How we have the 48 volt DC bus system, and on the DC bus system we have the batteries for the short term energy storage. Sometimes we call it as a buffer energy storage for voltage regulation point of view. And on the DC bus, through power conditioning devices, the primary renewable energy sources, they have been connected there. At the same time, electrolyzer and the fuel cell, they have also been connected to this power conditioning devices, that is, let's say DC-DC converter also. And then of course the load is there. And then overall here you can see that we need to have the appropriate control system for making the operation of the electrolyzer and the fuel cell, considering the energy level at the DC bus as well as the available energy from the primary renewable energy sources, as well as with reference to the load. Then there is a master controller and there are subcontrollers also. And then here you might have seen that electrolyzer is producing the pure hydrogen. That pure hydrogen has been stored at a particular pressure, okay, and reutilized in the fuel cell, but the oxygen, it went to the atmosphere. So now some of you might have thought, let's say, when we are considering the fuel cell operation, and for the fuel cell operation in the previous slides, I mentioned that the compressed air have been used as the oxidant. In place of compressed air, we can use the oxygen as the oxidant in the fuel cell. So naturally, when we use pure oxygen as the oxidant in the fuel cell, okay, then its efficiency or the performance is going to be improved. That is quite natural. And then another point which might have came to your mind, that when we are operating the electrolyzer, okay, then we have the hydrogen as a main output, then oxygen as a byproduct also. In the previous slide, you might have seen that here, this oxygen, it went to the atmosphere. But here in this slide, what we did, we captured the oxygen from this electrolyzer, we purified, filtered, and compressed at a particular pressure and used as the oxidant in the fuel cell. So previously I mentioned that we used the air as the oxidant into the fuel cell, but now we are using the oxygen in the as oxygen as oxidant in the fuel cell. So its performance or the operation is going to significantly improve. So here you can see that how there are different opportunities for learning as well as integrating different renewable energy system in a systematic way for storing the energy in the form of electrolytic hydrogen or making hydrogen as an energy carrier. But here this system has been treated as a standalone system, but we can make this system as a grid connected also. So here you can see that there is a lot of power conditioning devices are there and a lot of components are there. Every components are having very different operational characteristics. So when we consider integration of renewable energy system within the electrical energy network, so the topic is not only concentrating or covering only the electrical engineers, but it is also covering the chemical engineers, mechanical engineers, electronic engineers, control systems, and of course such type of system in future it will be remotely controlled. So ICT people, or we have to use anyway information communication technology for monitoring and operation in the cyber physical system also, right? So here you can see that how such type of project where we are trying to integrate different type of renewable energy sources, trying to have one energy carrier medium, let's say the hydrogen. So how this system is going to help us to integrate the different domain knowledge together. Okay, so that is a quite interesting here. Then one more point here, you might have noticed there is a programmable load also and programmable power source also. With the programmable load, we can create any type of situation and we can test this system. With the programmable power source, we can create any type of power generation scenarios and we can test this system in a very systematic way. It means that this system can be used as a test bench for testing like the operation or testing the performance of a system if we are going to have such type system in any place of the world. For example, we are going to have the system in Africa at somewhere, and we know that how the local resources or local energy resources production is going to be there. Accordingly, we can make the programming here in the programmable power source. And then we see that what type of how the load is going to change there. So accordingly, we can put programmable load here and test this system and find out how the different components or the subsystem components are going to perform or where we need to make some modifications and so on so forth. So this is a very interesting thing. So here on this slide, the specifications or the values of the different components of the renewable energy plants, they have been given. So let's say I mentioned that wind turbine, it was a 10 kilowatt 3-phase permanent magnet synchronous generator. Photovoltaic array, they were of 1 kilowatt capacity. Electrolyzer, it was alkaline electrolyzer. And buck converter, buck and boost converter, all of us, we know that it has multi-phase PWM based, okay, and DC load, programmable load, and similarly programmable power source also. And then of course the key point is storing the hydrogen. So hydrogen storage capacity was on the 10 bar, having total capacity of 3.8 meter cube, but we stored the hydrogen at the head bar from the safety point of view. And on the DC bus, there was a battery bank of 42.24 kilowatt hour. So that battery bank, basically it is helping us to as a reference point for making system operational and voltage regulation point of view also. And then another very important point, if we come back to this system, or maybe let's come back to this system, right? So you might have seen that, especially many of us we are from the electrical engineering background, and you might have seen that there is a lot of research work is going on the microgrid development, right? And in the microgrid also people are talking about AC microgrid and DC microgrid. So if you carefully observe here, so this system or the learning from this system can also contribute into the DC microgrid development also. Okay. Now here you can see that how this real system is there. So here you can see that this is a 5 kilowatt electrolyzer, 5 kilowatt fuel cell. This is a big cable here. It is for the wind turbine, small cable for the solar photovoltaic system. This computer, it has been worked as a master controller. This is a microcontroller for the electrolyzer. This is a microcontroller for the fuel cell. And here, this tank, it was a compressed air tank, and hydrogen storage tank, it was outside of the lab. So because we know that hydrogen is highly flammable, we have to be very safe, so it has been kept outside. Okay, and then here, this is the programmable power source and programmable load. And behind this, then we have this one big 50 kilowatt electrolyzer also. And now here you can see that this is a lab, a university-based lab. And then I developed this lab and I was working in Canada as well as in the Finland, also the same. And here you can see that all the electrical fitting in this lab, they are flame proof, because we know that hydrogen is highly flammable. If suppose there is a leakage of the hydrogen in this room by 2% by volume, right, then it is going to be highly flammable. So all electrical installations or all cabling and the switches, they should be flame proof, means there should not be any spark at all. Then another very interesting point is that we don't know, sometimes there may be accident or maybe leakage of the hydrogen. Okay, so we need to install a lot of hydrogen leakage detector sensors also. So these hydrogen leakage detector sensors, they help us if there is going to be any leakage into the system, then complete system is going to get stopped also. Even here, there was a possibility that if suppose by chance sensors didn't work and there is going to be continuous hydrogen leakage, then the roof of this lab is to get open, and then all the hydrogen is going to the atmosphere, because hydrogen is very lightweight, so immediately it will go up and we can avoid any accident. So basically here you can see that we have to work very heavily on safety also. And from the safety point of view, what I mentioned on the on one of the slide, that it has to be on top priority, and this safety issues, right, has to be considered very carefully when we are going to move towards the hydrogen oriented economy. So here these are the power conditioning devices which have been integrated between the electrolyzer and the DC bus, as well as fuel cell and the DC bus here. So here you can see some of the results also for a typical day, how the photovoltaic and wind power production was there. And during that typical day of operation, how the hydrogen has been produced and how the hydrogen has been consumed also through the fuel cell for producing the required amount of electrical energy that has been explained in this picture or in this graph basically. And then here you might have seen that hydrogen production is coming in the transient or in the cyclic way, that basically that hydrogen flow meter or measuring meter was installed after the compressor, and the compressor used to start in a cyclic way. So due to that, the hydrogen production measurement, they're coming into the cyclic way. But here you can see that everything is moving in a very transient way, and having all components different operational characteristics. And another thing which you might have noticed here in this slide, that electrolyzer and fuel cell, they were not operating simultaneously. So that is a very key point here. And during this one particular day of operation, here you can see that how the utilization factor or the energy efficiency of the compressor or fuel cell efficiency are represented on this slide, and then how the currents or the electrical current in the different components of the systems, how they were changing or varying with reference to the load or with reference to the setting operation of the electrolyzer and the fuel cell. They have been explained here. Okay, so as earlier I mentioned that DC source which we have has been taken here. So the DC source is going to help us to test such type of system, right? To test such type of system for considering climatic conditions of anywhere in the world, and we can test this system. Or in another way, in a simple way, if we want to test this system, and let's say nature is not favoring us, we don't have the wind or we don't have the solar photovoltaic solar energy available. So in that condition, we need the programmable source for testing this system. And then another thing which is very interesting and important for operation of such type of system is the energy level at the DC bus. So second point, basically it is defining or it is explaining the energy level at the DC bus for starting and stopping the operation of electrolyzer and the fuel cell, with condition that both of them, they should not work simultaneously. And then here in the first point, basically short-term energy storage is helping us for buffering or overcoming the intermittency of renewable energy sources. And in the second point, you might have seen that how much energy it has been stored in the form of hydrogen, and accordingly what was the utilization factor of the electrolyzer and the energy efficiency of the electrolyzer. And during the single day of operation, then in the previous slides when I have shown the results, you might have seen that the fuel cell operated, so how much the fuel cell has used hydrogen and how much energy they have been produced. And with reference to that, how much energy efficiency was there of the fuel cell and the utilization factor, they have been described. And when the load is there, of course, because we want to have the load and we want to test the system under the dynamic situation, so DC programmable load can help us to run the system or to operate the system under different situation or different conditions. Then here, then some more results are available for continuous operation of 28 days. So for 28 days, here you can see that how the renewable energy sources, they are contributing, and for during this 28 days period, how much electrolyzer input was there and how much fuel cell power output was there. So that is also quite interesting. And during this 28 days of operation, you can see that how this energy level at the DC bus, especially that buffer storage, buffer energy storage, battery bank, how they were varying, and the load variation also. Now here you can see that during this 28 days period, how the electrolyzer input power have been given, and correspondingly how the hydrogen production was there. So in short, you can see that, right, if we want to integrate the renewable energy system within the electrical energy system, and let's say our objective is to store the energy in the form of electrolytic hydrogen, and of course we will need the energy storage to overcome the intermittency of the renewable energy sources, then the hydrogen as an energy carrier can be a very good medium for storing the energy in the form of electrolytic hydrogen. And the results from this project this shows that the hydrogen production can be, or electrolytic hydrogen production can be achieved by using the developed control strategy and power conditioning devices. Another unique feature of this system is that so many different components with different operational characteristics are integrated through power conditioning devices on the DC bus, and they were working autonomously as per the defined control strategy. Then another learning point from this project is that the power conditioning devices which are required to interface between the DC bus and the electrolyzer, as well as fuel cell and the DC bus, right? So that can help us to transfer the power optimally from the DC bus to the electrolyzer and from the fuel cell to the DC bus. Then another very important point which was mentioned, next point, the energy level at the DC bus can help us for making the operation of the electrolyzer and fuel cell, right, autonomously and to avoid their simultaneous operation. And the system has shown very good safety, reliability, and performance record with electrolyzer efficiency and utilization factor also. Similarly, that has been given very good fuel cell efficiency and utilization factor. But we have to keep in mind this electrolyzer and the fuel cell efficiency, they are controlled by the electrochemical reaction. So due to that, we cannot change their efficiency. That efficiency is having a particular value because they are based on the electrochemical reactions, right? Only few percent, 1 or 2%, which we can improve. right? And then another thing which is very good, like when we tested this system at the different energy level at the DC bus and for the different load profile also, then it worked very well. So in short, or in conclusion, I can say that the operational encouraging experimental results from this standalone renewable energy system based on energy storage in the form of electrolytic hydrogen can contribute towards the hydrogen economy vision of many countries. And I believe that we are in future, maybe in let's say next 10 years or 20 years, this oil-based economy will be based on hydrogen economy. Depending on countries' infrastructure, in some countries it may go on the pure hydrogen, but in some countries like India, it may not go on pure hydrogen due to safety and reliability issue. But this hydrogen will be generated through the renewable energy sources and will be injected into the natural gas infrastructure or in the CNG infrastructure, and we will be going to have hydrogen, and we will be in a position to contribute effectively in reducing the CO2 emission or improving our environment. So thank you very much.
Thank you so much, sir, for the giving the detailed insight of the topic related to integrated renewable energy systems with energy. Discussed a lot very deeply about the hydrogen fuel cell, proton exchange membrane fuel cell, integration renewable energy system, and about the continuation of the last lecture, the European Union project, etc., about the solar hydrogen energy systems. And what I like the most is you have shared your project lab also that give the ambience of the research, actual project research. You have explained, you have shown that also, so that we can more connect to it, sort of. And and one thing which was very inspiring, which I found, that you told us that you have done a project, and after 20 years it has come into the commercial use. So research will take time, and so we need to continue with this uh, and keep on our efforts for the same. So the lecture is going is has many takeaways, sir, from participant views, from researchers' views. Uh, so I thank you so much for the session. And since you have been connected to us from morning 6 a.m. from your time zone till the almost half of the day. So thank you so much, sir. Now while the people are asking questions about for the session two, we have
Yeah,
two, three questions are remaining from the last session. So I
yeah,
would
yeah,
like to ask those questions. Can I take this question from one, sir? Okay.
yeah,
The
yeah, please.
two, three questions were remaining by chance. Mr. Avishkar Vanjari has asked two questions, that how the solar panel market in foreign countries as compared to India, and one more question from his side, that as a lot of foreign countries are mostly covered in snow, so why such solar panel manufacturing companies don't invest in India? This is the question from Avishkar.
Yes. I mean, in most of the developed countries, let's say, if you take the case of the Europe, the solar photovoltaic system, they are coming only on the roof mounted system. And then if you consider the Africa, right, there is a big potential and big land availability. So, and good solar resources also. So the next boom is going to come from the African side. And from the Indian side also, we have seen that there is a big market or big installations are happening on the solar photovoltaic system, but mainly on the higher capacity side, not only on the distributed network or on the roof mounted side also. And regarding the solar manufacturing sector, okay, so more, around 95% solar cells, they are manufactured in China because they have the capacity or they developed their industrial base like that. So in all over the world, around more than 95% solar cells, they have been supplied or provided by the China. And we have also seen that the cost is drastically dropping up. And regarding then cold climatic conditions, operation of the solar photovoltaic system. So in the previous session, you might have seen that I have given the annual PV production. So during the winter time, there was not any production from the solar photovoltaic system because it was a dark day and sunny, cloudy, and very small, few sunshine hours. But if you consider the summertime, we have the sunshine maybe let's say more than 20 hours. Sometimes even it is 22 hours also. So if you consider from the annual point of view, so we get a lot of electrical energy output from the solar photovoltaic system. And then another very interesting point from the cold climatic countries point of view, the operational temperature of the solar photovoltaic system is lower compared to the tropical region. So the efficiency of the solar cell also improves in the cold climatic region also.
Okay, thank you, sir. There was one more question from Akanksha Singh. Which is best in terms of power generation, solar botanic tree or normal panel installation?
Please repeat, what was the first one?
Which is the best in terms of power generation, solar botanic tree or normal panel installation? That is what
The normal panel installation is much better. A solar botanic tree is good from the architectural point of view. You have to have a good look and like that. But from the continuous generation or from the more capacity point of view, we have to put the panel based.
Okay, thank you, sir. We have the questions from this session now. Mr. Sandeep Pandan wants to ask that as compared with hydrogen generators and fuel cell, which one is better in terms of supply, the load, and why?
Fuel cell. Because with the help of the fuel cell, it is quite easy or good to monitor or to control the power output. It is going to be a stationary device also, and it has opportunities to operate as a combined heat and power system also. And if we use hydrogen in internal combustion engine, then it is going to be rotating part, and the efficiency is quite low, even 50% lower than the fuel cell.
Thank you, sir. This is the question from Mr. P.K. Gore. What is the lifespan of hydrogen fuel cell?
This is a very good question because at this moment is really difficult to say because the operational lifetime of the fuel cell depends on many conditions. If suppose we are not in a position to maintain appropriate humidification level or moisture level into the stack life is going to reduce it drastically. So if suppose if we are in a position to maintain the humidification level, in a position to supply the pure hydrogen, good oxidant, and maintaining the temperature and everything properly, then the fuel cell can have a good lifetime compared to the battery banks. That's why we are considering to store the energy in the form of electrolytic hydrogen from the long-term storage point of
view. Okay, sir. I think we have done with. I request all the participants as the session is going to end soon. If you have questions, put it in the chat box right now. Otherwise, the session is going to be concluded. I think, sir, we are getting nice feedback from the all the participants.
I think most of the participants, they are on the YouTube. I feel that, right?
Yes, sir. Because we have
Because in the first
so many numbers. Yes, sir.
Yes, in the first session, I noticed that on the YouTube link, there were around 500 likes on the link.
Yes, sir. There are so many. And because it's it would be difficult to handle so many participants here in the WebEx. It is
Yes,
in the capacity of 1,000, but from the ease point of view and
yeah,
technical suitability point of view, we have done it live, and it has the other advantage also that people, if some portion has been skipped or we have to revise, then we can refer that YouTube link
yeah. You
also.
can reorganize it, reedit it basically. Please do that one. Sometime like the voice may be not good or some disturbance may be there. So please reedit it and then repost again on the YouTube. Yeah. But I hope.
So Niti ma'am, the question answer, Niti ma'am.
Yes, ma'am, it has been ended now.
Okay. Thank you very much, Mohan Kole sir.
Thanks.
I am having feedbacks in the YouTube chat box. Very good session, sir. Nice session. Very interesting platform. Thank you so much, sir. Very informative session. So feedback excellent, sir.
Thank
And
you.
we have very nice experience with you, sir. First time we are interacting with you.
Yeah, I was planning many times when Ganga
Yes,
Madam
yes,
was there.
yes, sir.
She
Ji,
invited
sir.
me, and I think you might have written some couple of emails to me also. I
Okay,
don't
sir.
so I don't remember really the name, but someone
Yes, sir.
has sent me the email when Ganga Madam was there, and she I don't remember the name, but they
Yes,
mentioned
sir.
that some
Maybe
discount.
it may be possible. Yes, sir.
Huh?
Yes, sir. It may be possible.
Yes, yes, and
Sir, actually, in the
I was really planning, but this is but now Ganga Madam is no more. So I'm very sad that I didn't. I was not able to come when she was there. Yeah.
yes, sir. Sir, in the last week of August, we are planning for 1 week STTP. Same ICT approved on EVs, electric vehicles.
Yes. So I have one book
So,
on electric
yes,
vehicles
sir. I would like to invite you as a speaker.
that my book from LCWare, that is Electric Prospects and Challenges, first edition. It's quite a very good book. I will share that book with you, and maybe then I
Okay,
can highlight that book in the STT.
sir. So, sir, would you be able to give your slot for that period in the
Yeah,
last week of August?
no problem. I will help you.
As well as we will invite you for the inaugural also.
Yeah, yeah. No, I will help you there. No, sure.
Okay. So thank you so much, sir. If you want
Just
to share something, you can share, sir.
yeah, just give me the date, okay, so that I can put that date
Okay,
in
sir.
my
Okay, sir.
yeah.
Okay, sir. Ji, sir. Okay, sir.
Sure, sir.
So overall,
Okay.
everything was good.
Yes, sir. It was excellent. Not good.
Very good.
Yes, sir.
Because sometimes I worried about this communication and
No, sir. No, sir.
or internet quality. Or,
And sir, your way of teaching, you are very down to earth.
no,
Yes, sir. Yes, sir.
I'm from Madhya
We are
Pradesh.
very comfortable with you. We are very comfortable with you.
Yeah, because I'm born, brought up, everything in Madhya Pradesh. So,
Yes, sir.
and when Niti told me that about Ganga Madam, then I said, okay, I had to, because
Yes, sir.
I cannot say no then.
Okay. So thank you, sir.
Thank you.
Thank you so much, sir,
Thank you,
for
sir.
being here with us. And we'll be seeking your guidance in our future
Yeah,
research.
yeah. I will just
We'll
say,
be bothering you. Okay, sir.
Okay. Thank you, sir. Thank you so much.
my daughter, she was sleeping behind here. She was
Okay.
waiting for me when I finished.
Hello.
Okay, thank you.
Thank you, sir. Okay. Bye, sir.
Bye, bye, bye.
Okay. Good day, sir. Thank you so much for coming.
Okay, sir.
Thank you, everybody. Thank you, all the participants, for joining. The next session will be tomorrow, and we'll be having the distinguished guest, Professor Dr. Akhtar Kalam, with us with the tomorrow's session, as it has been mentioned here, and very known Dr. C.S. Solanki sir will be with us for the tomorrow's session. So all of the participants, thank you so much, and please join us tomorrow. Thank you everyone. Shall we end this meeting, ma'am?